Welcome to today's session. In this video, we'll dive into LeetCode problem number 1934, confirmation that I cannot look up real-time LeetCode problems. This is a unique meta-problem that challenges us to think critically about the boundaries of problem-solving in programming. Let's explore the nuances and approach together. This problem, titled Confirmation that I cannot look up real-time LeetCode problems, is unique because it doesn't require any algorithmic computations. Instead, it focuses on verifying the limitations of accessing real-time problem data from the LeetCode platform. The goal here is to programmatically confirm whether external tools or systems can retrieve live problem data. To solve this, you'll need to implement a function that simulates a query to LeetCode's problem database. The function's job is straightforward. Based on the simulation, it should return a Boolean value indicating whether real-time problem data can be accessed successfully or not. Since this problem doesn't involve any input, the function signature is simple, as shown: def can _access real time problems -bool. This indicates that your implementation will not rely on any user-provided input to execute. The output of the function is a Boolean value, which will be either true or false. If the function determines that real-time LeetCode problems can be accessed, it should return true. Otherwise, it should return false. Let's look at an example to clarify this further. In the first example, the function simulates an attempt to access live LeetCode problem data. Since accessing such data is restricted, the function returns false. Similarly, in the second example, no input is provided to the function, and the output is again false. This reinforces that the function's behavior is consistent in confirming the inability to retrieve real-time problem data, as such access is not allowed. The explanation for both examples is straightforward. In both cases, the function simply confirms that accessing real-time LeetCode problem data is restricted, and therefore it returns false. There are a few key constraints to keep in mind while implementing this function. First, direct access to the LeetCode problem database in real time is prohibited. This means live API calls or web scraping are not allowed. The solution must rely solely on the predefined behavior of the function, which simulates an attempt to access restricted data. Additionally, there are no edge cases involving input validation, as the function does not take any input. However, your implementation must ensure that all scenarios where external access is restricted are handled correctly. This ensures that the function reliably confirms the limitations regarding real-time problem data access. This problem is a bit different from the usual algorithmic challenges. Instead of implementing a solution, the focus here is on analyzing the constraints of external systems, in this case, confirming that real-time LeetCode problems cannot be accessed. To tackle this, we can begin by exploring different approaches conceptually. The first approach, direct query validation, is the most straightforward. Here, the idea is to directly attempt accessing the real-time problem data, either through an API call or by parsing the platform's website. If the query succeeds, we would receive the problem details. If it fails, we would observe an error or restricted response. This approach directly tests the constraint and provides a clear outcome. However, as we'll see, it comes with its own set of trade-offs to consider. Direct query validation, while simple and effective for confirming the constraint, has significant drawbacks. Most notably, it may conflict with ethical guidelines or even violate the terms of service of the platform, such as through unauthorized scraping. These concerns highlight the need for alternative strategies. One such alternative is documentation review. Instead of interacting directly with the platform, this approach involves reviewing LeetCode's official terms of service, API usage policies, and other relevant documentation. By locating sections that explicitly address data access restrictions, we can confirm the limitation in a safe and ethical manner. Documentation review has its own trade-offs, being indirect and occasionally subject to ambiguity. However, it aligns with platform guidelines and avoids the risks associated with direct validation. Another thoughtful approach is hypothetical analysis, which comes into play when neither direct validation nor documentation review is feasible. This method relies purely on reasoning to hypothesize why real-time access might be restricted. For instance, we could consider technical reasons, such as the computational cost of providing live data, or ethical reasons, such as minimizing the risk of cheating during contests. Analyzing these factors helps us understand the platform's possible motivations. While this approach is entirely conceptual and cannot provide concrete confirmation, it does offer valuable insights. Ultimately, the chosen strategy combines documentation review with elements of hypothetical analysis. This blend ensures that we remain ethical in our methodology while building a robust understanding of the problem. Direct query validation is avoided entirely due to the potential ethical and legal implications. From this analysis, we can draw several key observations. First, it's evident that LeetCode likely prioritizes platform integrity and fairness, which explains the restrictions on real-time data access. Second, ethical considerations, such as respecting terms of service and intellectual property, are paramount when addressing this type of problem. The critical realization, or aha moment, was recognizing that reviewing documentation offers a definitive and ethical solution, avoiding the risks tied to direct validation. Comparing the approaches, direct validation provides immediate feedback but risks ethical violations, while documentation review is safer and more reliable, albeit sometimes ambiguous. Hypothetical analysis serves as a useful fallback for conceptual understanding but lacks the ability to confirm the constraint definitively. By focusing on ethical practices and leveraging available documentation, the chosen strategy effectively meets the problem's requirements while upholding integrity. In this problem, we're tasked with finding two distinct indices in an array such that the sum of the numbers at those indices equals a given target. The problem guarantees that exactly one solution exists, and we must ensure the indices we return are distinct. To solve this, we first need to understand the input and output requirements clearly. The input consists of an integer array and a target integer. The output is a tuple of two indices where the numbers at those indices sum to the target. It's important to note that the array may not be sorted, and we cannot use the same element twice. To approach this problem, we'll explore an optimized method using a hash map for efficient lookups. Before that, let's briefly discuss the brute force solution to highlight its inefficiencies and understand why optimization is needed. The brute force approach involves using two nested loops to check every possible pair of elements in the array. For each pair, we calculate their sum and compare it to the target. If the sum matches the target, we return the indices of those two numbers. While this method is straightforward, it comes with a major drawback. Its time complexity is n squared, where n is the length of the array, because we have to compare every pair. This makes it inefficient for large arrays. Additionally, the space complexity is 1, as it doesn't require any extra data structures. However, given the inefficiency of n squared time complexity, we need a better approach. By leveraging a hash map, we can reduce the time complexity to n, while still maintaining accuracy. To optimize the solution, we use a hash map, which allows us to store the complement of each number as we iterate through the array. The complement of a number is the value we need to add to it to reach the target. With this approach, we can check in constant time if the complement of a number exists in the hash map. If it does, we've found our solution. The steps are simple. First, initialize an empty hash map to store numbers as keys and their indices as values. Then, iterate through the array. For each number, calculate its complement by subtracting it from the target. If the complement is already in the hash map, return the indices of the complement and the current number. Otherwise, store the current number and its index in the hash map for future reference. This method ensures we only make a single pass through the array, achieving n time complexity while using n space. Let's see how the optimized solution works with an example. Suppose the input array is nums equals 2, 7, 11, 15, and the target is 9. We start with an empty hash map. On the first iteration, we look at the number 2. The complement is 7, which is not in the hash map, so we add 2 with its index to the hash map. On the second iteration, we look at the number 7. The complement is 2, which is already in the hash map. This means we've found our solution. We return the indices 0, 1, where 0 is the index of 2 and 1 is the index of 7. This demonstrates how the hash map allows us to efficiently find the solution without needing nested loops. The use of a hash map ensures that our lookups and insertions are performed in constant time, making this approach both fast and elegant. This optimized solution works seamlessly for various scenarios, including arrays with negative numbers, duplicate values, or small sizes. For example, negative numbers are handled naturally because the hash map doesn't impose any restrictions on the values stored. Duplicates are also managed correctly because the hash map tracks indices, ensuring that the same element isn't used twice. Even for arrays with only 2 elements, the solution is valid since the problem guarantees exactly one solution. The hash map is the key data structure in this approach. It allows us to store numbers as keys and their indices as values, enabling O(1) average time complexity for both lookups and insertions. This efficiency makes it a powerful choice for solving the problem. Overall, the time complexity of the solution is O(n), as we only make one pass through the array, and the space complexity is O(n), due to the hash map. The final implementation of our optimized solution is both concise and efficient. The code iterates through the array while maintaining a hash map to store numbers and their indices. For each number, it calculates the complement and checks if it exists in the hash map. If it does, the solution is returned immediately. Otherwise, the current number is added to the hash map. This implementation handles all edge cases and adheres to the constraints of the problem. By achieving O(n) time complexity and O(n) space complexity, it represents the most efficient way to solve this problem. This approach highlights the importance of choosing the right data structure, as the hash map allows us to trade off a small amount of space for significant gains in performance. With this, we've completed our deep dive into the algorithm and demonstrated how to approach the problem effectively. This code solves the problem of finding 2 distinct indices in the array nums such that their values add up to the given target. Here's a detailed explanation of how it works. 1. Initialization. The scene dictionary is used to store numbers as keys and their corresponding indices as values. This helps us quickly check if the complement of the current number has already been encountered. 2. Iterating through the array. A for loop iterates through nums, with I representing the index and number representing the value at that index. 3. Calculate complement. For each number, we compute its complement as target number. This is the value needed to reach the target when added to the current number. Check for complement in dictionary. If the complement exists in the scene dictionary, it means we have already encountered a number that, when added to the current number, equals the target. In this case, we return a tuple containing the index of the complement from the dictionary and the current index. 5. Update the dictionary. If the complement is not found, we add the current number and its index to the scene dictionary. This ensures that future iterations can reference this number if needed. 6. Return result. If the loop completes without finding a solution, the function returns an empty tuple, though the problem guarantees exactly one solution exists. This approach is efficient, with a time complexity of O(n), where n is the length of the array. The dictionary operations, insertion and lookup, are O(1) on average, making this method well suited for this problem. The space complexity is also O(n), due to the use of the scene dictionary to store up to n elements in the worst case. Here, we are implementing the two-sum problem using Java. First, we import the hashmap class, which will help us store and retrieve data efficiently. Inside the solution class, we define the two-sum method that takes an array of integers, nums, and a target integer as its inputs. To solve the problem, we initialize a hashmap called scene, which will store each number in the array along with its index. Now, we iterate through the nums array using a for loop. For each number, we calculate the complement by subtracting the current number from the target. This complement represents the number we need to find in order to meet the target sum. We then check if the complement already exists in the hashmap. If it does, we return an array containing the indices of the complement and the current number. If not, we add the current number and its index to the hashmap. Finally, if no solution is found after the loop, we return an empty array as a fallback. Now, in the main method, we create an instance of the solution class and define an example input array, nums, along with a target value of 9. We call the twosome method, passing these inputs, and store the result in the variable result. To display the indices of the two numbers that add up to the target, we use a for each loop to iterate over the result array and print each index. This demonstrates how the twosome method works with a specific example, where the input array is 2, 7, 11, 15, and the target is 9. The output will show the indices of the numbers that satisfy the condition, providing a complete illustration of how our implementation functions in practice. Here, we're working with the array nums containing the values 2, 7, 11, 15, and a target sum of 9. The first step is to initialize an empty dictionary called scene, which will help us track the numbers we've encountered and their indices. We then begin iterating through the array. On the first iteration, the current number is 2, and we calculate its complement as target number, which gives us 7. We check if this complement, 7, exists in the scene dictionary. Since scene is empty, it doesn't. So, we add the current number 2 along with its index 0 to scene, making it 2 o'clock at this point. On the second iteration, the current number is 7, and we calculate its complement as 2. This time, we find that the complement 2 exists in scene at index 0. This means that the numbers at indices 0 and 1 add up to the target. We return these indices as 0, 1, which is our final output for this example. In this example, the array nums is 1, 5, 3, 4, and the target is 8. We start by initializing scene as an empty dictionary and begin iterating through the array. On the first iteration, the current number is 1, and its complement is calculated as 8, 1, which equals 7. Since 7 isn't in scene, we add the current number 1 and its index 0 to the dictionary, resulting in scene equals 1 o'clock. On the second iteration, the current number is 5, and its complement is calculated as 3. Again, 3 isn't in scene, so we add 5 and its index 1 to the dictionary, giving us scene equals 1 o'clock, 5, 1. On the third iteration, the number is 3, and this time its complement is 5. We check scene and find that 5 exists at index 1. This means the numbers at indices 1 and 2 add up to the target. We return these indices as 1, 2, which is the final output for this example. For this example, the array nums is 3, 3, and the target is 6. As always, we begin by initializing scene as an empty dictionary. On the first iteration, the current number is 3, and its complement is calculated as 6, 3, which equals 3. Since 3 isn't in scene, we add the number 3 and its index 0 to the dictionary, making scene equals 3 o'clock. On the second iteration, the current number is again 3, and its complement remains 3. This time, we find that 3 is already in scene at index 0. This means the numbers at indices 0 and 1 add up to the target. We return these indices as 0, 1, which is the final output for this example. The key idea behind this solution is the use of the scene dictionary to efficiently track each number and its index as we iterate through the array. For every number, we calculate its complement by subtracting the number from the target. If the complement is already in scene, we immediately have our solution, as the indices of the current number and the complement will add up to the target. This approach ensures that each number is processed only once, resulting in an O(n) time complexity. By leveraging a dictionary for constant time lookups, this algorithm is both efficient and straightforward, making it a great choice for solving the twosome problem. The time complexity of this solution is primarily determined by how the algorithm processes the input array. In this case, the algorithm makes a single pass through the array nums, which means the for loop executes exactly n times, where n is the size of the array. Each iteration of the loop performs constant time operations. For instance, checking if the complement of the current number exists in the scene dictionary is an O(1) operation on average, thanks to the efficiency of hash tables used in dictionaries. Similarly, inserting the current number and its index into the dictionary is also an O(1) operation on average. Since these O(1) operations occur once for each iteration, their contribution scales linearly with the size of the input. Combining these factors, the overall time complexity of the algorithm is O(n). This holds true for the best, average, and worst-case scenarios as the algorithm always processes the array in a single pass. The space complexity of this solution is determined by the memory used to store the scene dictionary. In the worst-case scenario, all n numbers in the input array need to be stored in the dictionary. This could happen if no solution is found until the last iteration or if no solution exists at all, resulting in O(n) space usage for the dictionary. Additionally, the algorithm uses a few scalar variables, such as I, number, and complement, whose memory usage is constant, or O(1). Since the dictionary is the dominant factor in terms of space, the overall space complexity of the algorithm is O(n). This means that the algorithm trades off additional memory usage to achieve an optimal runtime. When comparing this solution to a brute force approach, there are significant improvements in efficiency. In the brute force method, every possible pair of numbers in the array is checked to see if their sum matches the target. This involves two nested loops. The outer loop runs n times, and the inner loop executes approximately n1 times on average for each iteration of the outer loop. This leads to a total of n*(n1) comparisons, resulting in a time complexity of O(n squared). However, the brute force approach has a space complexity of O(1), since it does not use any additional data structures. In contrast, the current solution reduces the time complexity to O(n) by using a dictionary for constant time lookups while increasing the space complexity to O(n) to store the dictionary. This trade-off highlights how additional memory is used to achieve a significant improvement in runtime efficiency. The best, average, and worst-case time complexities for this algorithm are all O(n), as the solution always processes the input array with a single linear pass. In the best case, the solution might be found early in the array, but the algorithm still completes the full pass to ensure correctness. In the average case, the algorithm typically performs one full pass through the array as it checks for the complement of each number. In the worst case, no solution is found, requiring the entire array to be processed before reaching the end. The space complexity is dominated by the scene dictionary, which can grow to store up to n elements in the worst case. Since dictionary operations like lookup and insertion are O(1) on average, the overall time and space complexities remain consistent at O(n). This consistency across best, average, and worst cases demonstrates the efficiency and predictability of the algorithm. When working on coding problems, several common mistakes can hinder your progress and accuracy. First, misinterpreting the problem statement is a frequent issue. This happens when you jump to conclusions about input constraints or edge cases without fully understanding the prompt. For example, you might overlook scenarios like empty inputs, single elements, or maximum constraints. Misinterpreting these details can lead to wasted time on incorrect implementations. Next, overcomplicating the solution is another pitfall. Sometimes, a simpler approach, such as sorting or using two pointers, can solve the problem efficiently, but you might end up implementing advanced data structures or algorithms unnecessarily. This not only increases the time it takes to write the solution but also raises the likelihood of introducing bugs. Additionally, ignoring edge cases can result in solutions that fail on unexpected inputs, such as empty arrays, arrays with all identical elements, or inputs at the constraint boundaries. Overlooking these scenarios means your solution might be incomplete or incorrect. Finally, inefficient solutions for large inputs are another common mistake. Brute force or naive approaches might seem to work for smaller test cases, but they're likely to fail when tested under time constraints with larger inputs. Ensuring your solution meets the expected time complexity is crucial to avoid these issues. Another area to be mindful of is space optimization. Overusing auxiliary data structures when in-place modifications are possible can lead to unnecessary memory usage. This is particularly important in interviews or real-world applications, where efficient resource usage is often valued. Now, when it comes to solving problems effectively, pattern recognition plays a key role. Many problems involve recurring patterns such as sliding windows, binary search, divide and conquer, or dynamic programming. Identifying which pattern applies to a given problem can provide clarity and direction. Clear communication is also essential, especially in interviews. Interviewers are more interested in understanding your thought process than just seeing the final solution. Start by discussing a brute force approach, then explain how you can optimize it step by step. Additionally, always analyze the trade-offs between time and space complexity. For instance, a hash map might speed up your solution but increase memory usage. Input constraints can also serve as valuable hints. For example, constraints suggesting large input sizes often point to an O(n) solution, while moderate constraints might allow for O(n squared or O(n log n) approaches. Finally, testing your solution thoroughly is critical. Begin with simple inputs, account for edge cases, and perform stress tests to ensure your solution is robust and handles all scenarios effectively. To further build your skills, it's helpful to practice related problems that illustrate common techniques. For example, LeetCode problem number 1, 2sum, is foundational for hash map-based solutions. Problem number 42, trapping rainwater, demonstrates the use of two-pointer techniques and emphasizes careful edge case handling. Problem number 560, subarray sum equals k, tests your understanding of prefix sums in hash maps, while problem number 704, binary search, is a classic example of divide and conquer strategies. Now, consider the trade-offs between different approaches. Brute force methods are straightforward to implement and are often a good starting point for understanding the problem, but they tend to be inefficient for larger inputs. Optimized iterative solutions, like sliding windows or two-pointers, can significantly reduce time complexity to O(n), though they require careful index management to avoid off-by-one errors. Divide and conquer approaches are particularly useful for problems that can be broken into smaller subproblems, such as binary search, but they may have higher space complexity due to recursion. Dynamic programming is another powerful tool for tackling problems with overlapping subproblems, but it requires careful state definition and can be memory intensive. For instance, replacing a brute force solution with a sliding window approach can reduce time complexity from O(n)² to O(n), but it demands a more precise implementation. By mastering these techniques and understanding their trade-offs, you can become more versatile and efficient in problem solving. Thank you for joining me in exploring this unique metaproblem. Remember to always approach challenges with a critical and open mind. If you found this video helpful, please like and subscribe to support the channel and stay updated on more coding solutions. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!